Hello, gentlemen. Welcome back. This is going to give you guys a brief introduction to calculus. We're going to look at some of the things that you're going to see right at the beginning of the school year, which are going to concentrate on limits. I'm going to introduce you to the concept of limits. I'm going to show you how to, some simple techniques to evaluate limits. Then we're going to talk about the tangent line problem, which is going to lead into differentiation. And these topics are going to really be the bulk of your first semester in either honors or regular calculus. So it can be a little bit intimidating. Just try to follow along. I know it's been a busy summer, but these topics are important, and hopefully you'll see that they're not too bad. Okay, let's talk about limits. So let's start there and talk about what what a limit is. All right, so let's talk about the basics. Okay, we're looking for the behavior of a function, and we've studied functions all year as x approaches some value of c. Okay, and so we looked at this a little bit. We looked at the function of trigonometric functions, say like the tangent functions, as we approach that vertical asymptote pi over 2. All right, so we can use this idea of a limit to really describe the behavior of a function as x approaches some value. We say if x becomes arbitrarily close to a single value L as x approaches c from either side, the limit of f of x as x approaches c is equal to L. That's basically what it means. We'll talk about this idea of either side coming in from the left and from the right in a bit. But this is essentially what it means. And mathematically, we're going to write this is read the limit as x approaches c. C can be some number. X approaches 5, let's say, of f of x is equal to L. And so that means that as this function gets really close to c, from either the left or the right, the function value is approaching this value of L. That's what it means. Okay. The existence or non-existence of a function at c has no impact on whether or not the limit exists. A function can not be defined, but still the limit exists. For example, let me get my pen out here. Here's a situation where if I had a function with a hole in it, if I had a straight line like that, hole, and then my line continued. As I approach, as this function is not defined at that point for some reason or another, it might not be in the domain. It might be a rational function where the denominator got factored out. But in any event, the limit as I approach from the left and the right, the function is going to get closer and closer to whatever this value is. It's not going to equal it, but I'm going to get close to it. So the limit there would actually equal whatever that value is. Let's say it's L. Okay, so don't understand that just because a function is not defined there, or maybe it's defined up here, the limit can still exist. Okay, that's a tougher concept to understand, but we'll see an example in a second. For a function exists, it must approach the same value from the left and the right, and that's what this is shown right here. This here with the negative sign right there, this side right here, is taking the limit from the left. From left here, and this one's from the right. And I know it's from left and right because of the plus sign right there and the minus sign. So if I'm taking the limit as x approaches c with a minus sign, that means I'm coming in from the left side. So again, if I'm looking at a graph and I'm looking at something like that, and I want to find the limit as I come in there, if I come in from the left, I'm going to come in this way, a little bit less than values of, let's say, 6. So if I'm coming in and want to find the limit as x approaches 6, I'm going to think about values like 5.999, something really close. And if I come in from the right, I'm coming in from that side. Okay, that's what it means to come in from the left and the right. And in order for that limit to exist, it has to be the same from both directions. Let's look at a situation where limits don't exist, because the limits don't always exist. There's 3 situations that we're going to look at. One, we approach a different number from the left and the right. These one-sided limits that I just mentioned. If I look at this piecewise function here, and I'm coming in from this side, which would be from the left, and I come in from this side from the right, what we're going to see is we're going to approach 2 different values. Okay? If I come in from the right, if I'm coming in from this side, if I'm a little bit greater than 2, I'm using this part of the function right here, and I'm going to approach a value of 1. As I come in, get closer and closer, I'm getting closer and closer to the value 1. I actually am equal to 1 there. Okay? But if I come in from the left, if I'm coming in from this side, 1.999, I'm using this top part of the function, and I'm going to approach a value of 4. Okay, so from this side, it looks like I'm approaching from 4. From this side, it looks like I'm approaching from 1. Because those are different, because I get a different value from the left and the right, I'm going to say that the function, the limit, does not exist. Okay? In order for the limit to exist, I must approach the same number from the left and the right. So there's one situation where a limit will not exist. Another one is going to be a function increases or decreases without bound as x approaches c. Look at this value, function 1 over x minus 3. You guys should all realize that I'm going to have vertical asymptote at x equals 3 because I'll have 0 in the denominator. If I look at approaching 3 from the right, as I'm coming in this way, this is going to grow without bound. Okay, this is actually going to go off to positive infinity because I'm going to get 1 divided by a really small positive number. Remember, I'm coming in, I got 3.00001, something of that nature. So I'm going to get a really small positive number in the denominator, and so I'm going to go off to positive infinity here. Okay, does not exist. If I come in from the left, this way, again, it's not going to exist, but I'm going to head towards negative infinity because the denominator is now negative 0.00001, something like that. So I'm going to have a negative in the denominator. I'm going to approach negative infinity right like that. When I grow without bound, I usually state if it's going to positive infinity or negative infinity, but understand that the limit doesn't exist. All right. Also note here that the left and the right hand limits don't exist, aren't the same either. Okay, so there's another example of that. Okay, so my conclusion is that this limit does not exist. And the third one is going to be where a function oscillates between two fixed values. Okay, so something like this. If I look at the cosine function, and I'm interested, what happens to the cosine function as x gets huge. All right, and I know that cosine is periodic. I know that its values oscillate between 1 and negative 1. So as x goes off to infinity, I'm just going to have this function go bouncing up and down. It's not going to approach one specific number, and therefore we're going to say that the limit does not exist. Okay, so there are 3 situations where the limit did not exist. All right, one was when the left and right hand limit didn't approach the same number. The other was when we grew without bound, and the other is when we had a function that oscillated between two values. Here are some simple properties of limits, and again I'm going to show you some properties on this page and the next. Make sure that you understand them. The limit of a constant function as x approaches c is simply equal to that constant. That should be really straightforward. That says this. Constant function looks like that. No matter what x value I approach, the function value is going to be equal to that b value, whatever it is. Okay? The limit as x approaches the c of x, the straight line x, is equal to c. Again, that should make sense. Let's see if I can get a good line there. Yeah, it's pretty good. No matter what value I approach for c, the function value, this is f of x equals x, the function value is going to approach that value of c. Okay, so that should make sense. And this is similar to that. Limit as x approaches c of x to the n is simply equal to c to the n. All right, so if I had something like a parabola, like that, and this was x squared, and I wanted to know the limit as x approaches 2 of f of x, I'm just going to get 2 squared or 4. Okay? So those hopefully are pretty straightforward. You guys understand them. Make sure you get those. We'll do a little practice at the end of this. A couple other ones that you need to know. Let b and c be real numbers, n be a positive integer, and let f and g be functions such that the limit as x approaches c of f of x is equal to L, and the limit of g of x as x approaches c is equal to k. This is the scalar multiple rule. The limit as x approaches c of b times f of x. I can simply bring that b out. In other words, I could rewrite this right here to be equal to b times the limit as x approaches c of f of x. And we know that this part here is equal to L, and that's where it became B plus L. Here I can write this and break them up. I can write this as the limit as x approaches C of f of x plus or minus the limit as x approaches C of g of x. And we know that f of this limit is L, this limit is K, so it's L plus or minus K. Same thing here. I can rewrite this as the limit as x approaches C of f of x times the limit as x approaches C of g of x, and that's just L times K. Same thing with quotient, except with division. I got to make sure that K is not equal to 0. And then if I have a power, I can rethink this one as the limit as x approaches C of f of x, and I can raise that whole thing to the nth power like that. Okay, so just some different properties that you guys need to make sure that you understand. Let's do a couple examples. Given that x approaches C of f of x is equal to 27, and the limit as x approaches C of g of x is equal to 1/3, I want to know the limit of x approaches C of 2 times f of x. Here I can break that up. I can write this as 2 times the limit as x approaches C of f of x, which should be 2 times 27, which is 54. Okay. The sum here, I can look at this, writing this out as the sum of two different limits. Okay. I know that this one's 27. I know that this one's 1/3. So I can add those and get 82/3. Okay. F of x times g of x. Again, I can rewrite that as the limit as x approaches C of f of x times the limit as x approaches C of g of x, like that, and I get 27 times a third, or just 9. And then finally, if I want to take the cube root, it's like taking the cube root of this limit here, so it's the cube root of 27, which is simply equal to 3. Okay? So there's some quick introduction to limits. Okay, these are going to be a really important part of calculus. They're going to help us with what we call the tangent line problem, which we'll see in a couple videos. The area problem, it describes the behavior of functions as x approaches certain values, a given value C. We looked at the when limits do not exist. We talked about one-sided limits, making sure that the limit from the left and the right is the same in order for the limit to exist. And then we'll learn some techniques about evaluating limits. All right, so there's a quick introduction to it, fellas. The next video we'll look at a little bit further in depth some different steps that you take to evaluate limits and some different techniques. And then we'll do one more video after that on tangent line problems. Okay? Any questions, make sure you go into the Google Hangout sessions or email me. All right, fellas, have a good day.